Hello everyone, and welcome to Geometry Lesson 4.4, the Pythagorean Theorem and the Distance Formula. In our last lesson, we talked about special properties and theorems involving isosceles and equilateral triangles. We'll be moving on to right triangles in this lesson, but let's review a few of the concepts from last time first. In our first review problem, we're given 3x and 36 as two of the side lengths in a triangle. We're also shown that the angles opposite those sides are congruent. Remember, the converse of the base angles theorem tells us that the sides opposite those congruent angles must also be congruent, so we can write the equation 3x equals 36, since congruent means equal. Dividing both sides by 3 gives us x equals 12. In the next problem, we have an equilateral triangle with all three sides congruent. Remember, equilateral means that it's also equiangular. Equiangular means all three angles are congruent, so we have three angles, all the same, that have to add up to 180 degrees. 180 divided by 3 gives us 60 degrees for each of those angles. You might remember from our last lesson that we made a rule that every equilateral and equiangular triangle has three 60-degree angles. In this problem, one of the angles is marked 4x. Knowing that angle must be 60 degrees, we can write the equation 4x equals 60. Dividing by 4 on both sides leaves x equals 15. One more review problem before we move on to some new stuff. This time I have an isosceles right triangle. That right angle already takes up 90 degrees, so I only have 90 degrees left for the other two angles. The base angles theorem says that those angles that are opposite the congruent sides must also be congruent. Putting all of that information together, I can see that I have two congruent angles whose sum is 90 degrees. So I just have to divide 90 by 2, and that leaves 45 degrees for each angle. Alright, that's enough review, so we can move on to today's fun and exciting lesson. Let's start with right triangles. Remember from section 4.1 that a right triangle is a triangle with one right angle. Right triangles have a lot of really interesting properties and relationships. Just like isosceles triangles, right triangles have some special terminology. Only right triangles have a side called a hypotenuse. The hypotenuse is always the longest side of a right triangle. It's always opposite of the right angle. The other two sides are called legs, just like the congruent sides of an isosceles triangle. In this triangle, the hypotenuse is the side opposite the right angle. That means it's the only side I can trace that won't touch the right angle. When you're working with right triangles, it's a good idea to find and label the hypotenuse as your first step. Now that we know what makes a right triangle special, we're ready for some theorems. The first one's a doozy. The Pythagorean Theorem is probably the most well-known theorem in all of geometry, and for a good reason. It's a basic building block for many other theorems, properties, proofs, and understandings that we'll have. The Pythagorean Theorem says that in a right triangle, the square of the length of the hypotenuse is equal to the sum of the squares of the lengths of the legs. So let me start by highlighting the words right triangle. The Pythagorean Theorem can only be used with right triangles. Now I'm sure you'd like a little more explanation on the theorem itself. In an equation, it would look like this. Leg squared plus the other leg squared equals the hypotenuse squared. Still don't recognize it? Let's look at this right triangle for some help. Let's call the legs of the triangle A and B, and we'll call the hypotenuse C. Plugging them in gives us the most popular version of the Pythagorean Theorem. A squared plus B squared equals C squared. As a quick example, let's say A equals 3 and C equals 5. Now the most important thing to remember is that A and B are legs, and C is always the hypotenuse. Putting 3 in for A and 5 in for C gives us 3 squared plus B squared equals 5 squared. Here we'll be solving for the length of the other leg, B. The hypotenuse always has to be on the side by itself, so I know 3 squared is 9 and 5 squared is 25, so we'll have 9 plus b squared equal to 25. Subtracting 9 from each side leaves us with b squared equal to 16. To solve for b, we need to figure out what number times itself equals 16. That means taking the square root of both sides. Hopefully you remember from algebra that squares and square roots are inverse operations. They undo each other. That leaves us with b equal to the square root of 16, which is 4. When we solve equations with square roots, we usually leave a plus or minus in our answer, but since this is a length, it has to be positive, so we can disregard the negative case. One more thing before we move on to some examples. Did you notice how convenient the numbers in our practice problems were? 3 squared plus 4 squared equaled 5 squared. They were three whole numbers that satisfied the Pythagorean theorem. Any set of 3 whole numbers that work in the Pythagorean theorem are called a Pythagorean triple. Finding and memorizing Pythagorean triples could save you a lot of time and effort in the months to come. Once you find a triple that works, every multiple of those numbers works as well. Take 3, 4, 5 for example, the triple we just used. Multiplying each number by 2 gives us 6, 8, 10, another Pythagorean triple. You don't have to memorize or learn Pythagorean triples, but I think you'll find them rather handy. Now on to those practice problems. In our first problem, we have one side labeled 6 and one labeled 10. So our first step is to find the hypotenuse. It's the one opposite the right angle, so 10. That means 6 squared plus b squared equals 10 squared. 6 squared is 36, 10 squared is 100, so we'll have 36 plus b squared equals 100. Subtract 36 from both sides, and we'll have b squared equal to 64. Take the square root of both sides, so b equals 8. Next we have a triangle with two sides labeled 5 and 5. Find the hypotenuse first, so it would be c on this triangle. Now I have 5 squared plus 5 squared equals c squared. Remember that hypotenuse is always by itself. 5 squared is 25, so we have 25 plus 25 equals c squared. To solve for c, we need to take the square root of 50. We can simplify this a little bit by taking out any perfect square factors of 50. 50 is equal to 25 times 2. Since 25 is a perfect square, we can take the square root of that, which is 5. The 5 will come out of the root and the 2 stays inside, so we'll have 5 square roots of 2. If you're having trouble simplifying that square root or didn't understand that at all, don't worry, we'll review that in class and in another video. For now, just focus on getting to the root. One last example before we move on to the distance formula. Here we have a triangle with sides labeled 15 and 17. The hypotenuse is 17, so our equation will be 15 squared plus a squared equals 17 squared. Here's where a list of perfect squares might be nice to keep on hand. Up to 20 should be enough to do most of the problems that we'll have. 15 squared is 225, and 17 squared is 289. Subtracting 225 from each side gives us a squared equal to 64. Taking the square root of each side leaves us with a equals 8. Notice anything about that problem? All whole numbers again. So you better add 8, 15, and 17 to your list of Pythagorean triples. Let's look at this graphically for a minute. Here we have a triangle on the coordinate plane. None of the sides are labeled, but we're asked to find each side length. Let's start by labeling the vertices. This top one is -7, 8, the bottom is -7, -8, and the right side is 5, -8. Now with the sides that go straight up and down, or straight left and right, we can just count the units. But what about that long diagonal side? The diagonal of a square is longer than any of its sides, so we can't just count up the diagonals this time. Instead, we'll need some math. Hooray! Let's find the length of those other two sides first. Now we could just subtract the y-coordinates to get the length of the segment on the left that goes up and down. Or if you'd rather save your brain up for the next part, then just count the squares. Either way, that side measures 16 units. The horizontal side that goes from left to right measures 12 units. Since vertical and horizontal are perpendicular, this has to be a right triangle. If we put this in the Pythagorean theorem, we have 16 squared plus 12 squared equals c squared. That hypotenuse is the diagonal. Simplifying that gives us 256 for 16 squared, 144 for 12 squared, added together to equal c squared. So we'll have 400 equals c squared, and taking the square root of that leaves c equal to 20. That example showed us how we can use the Pythagorean theorem to find the distance between any 2 points, but we don't have to draw a triangle every time. As it turns out, there's a formula for that too, the distance formula. The distance formula comes from the Pythagorean theorem, but we'll save the explanation of that for another video. The distance between any 2 points is equal to the square root of the difference in the x-coordinate squared, added to the difference in the y-coordinate squared. Sound complicated? Let's try it and see how it works. First, we're asked to find the distance between the points 0, 0 and 3, 4. I'd suggest starting these problems by labeling the points x1, y1 and x2, y2. That way you'll always know where each number belongs in the formula and things can't get turned around on you. Then all that's left to do is plug the numbers in and simplify. So here we go. In our first example, x2 is 3 and x1 is 0. So we'll have the square root of 3 minus 0 that squared added to the difference in the y-coordinates. y2 is 4 and y1 is 0, so that's 4 minus 0. And then square that. The distance between the points is the square root of 3 minus 0 squared plus 4 minus 0 squared. Simplifying the subtractions leaves us with the square root of 3 squared plus 4 squared. 3 squared is 9 and 4 squared is 16, so now we've got the square root of 25, or 5. Let's try another one. In this example, x1 is negative 2, y1 is 2, x2 is negative 3, and y2 is negative 3. It doesn't matter which point we call x1, y1, and which one we call x2, y2. We just have to make sure that the 1's are in the same pair and the 2's are in the same pair. Plugging our coordinates into this formula gives us the square root of negative 2 minus negative 3. And then squaring that, adding it to 2 minus negative 3 squared. Simplifying those subtractions gives us 1 squared plus 5 squared. That's 1 plus 25, or the square root of 26. This one can't be simplified anymore, so we'll just leave it like that. Nice work! That's it for lesson 4.4. This lesson covered a lot of information, so be sure to take the time to go back and review any parts of the lesson that you didn't understand or that you'd like a second look at. As always, thanks for watching and happy hypothesizing.